Okay, so I am very pleased to have the privilege of introducing our speaker, Angelo Janabi, who's going to present his Master's of Science research today. Angelo was born in Manoa in the Philippines and moved to the US at the age of 10. He grew up in Silicon Valley in the heart of the tech industry, but he found himself drawn to geology in college, and he earned his Bachelor's of Science in Earth Sciences from University of California in Santa Cruz. And then he went on to work in industry for a few different geotechnical firms in California before he decided to come to our department for his master's degree. I have to say that I actually really like getting students who've been out in the workforce because they're very focused on getting to their goals. And Angelo has been a great example of that. He was interested in working in extraterrestrial materials, on extraterrestrial samples, and was talking to faculty in the Hawaii Institute of Geophysics and Planetology. And I managed to lure him down into the dungeon, the basement, into our basement lab to use ion and electron microscopes. So while he's been here at UH, he has performed remarkably well in his classes and in his research. He earned an outstanding 4.0 GPA on his coursework. Angelo has proven himself to be very smart and very quick to learn and apply new concepts and new complex instrumentation. He doesn't flinch from hard work. The microscopy work you're going to see today was carried out manually with sheer determination and brute force, and it really provides a solid foundation for the future of our cosmic dust collection here in Hawaii. Angelo asks the right questions and he follows up, and I think that his curiosity and his drive to really understand what he sees goes to the heart of research. And as you'll see today, he has great communication skills, which are so critical in research as well as in any other career. And I wish Angelo were staying with us longer, but with his knowledge and skills and capabilities, he's already landed a job after graduation right here in Honolulu with AECOM as an environmental scientist. And with that, I'm very proud to turn over the cyber microphone to Angelo Janabi.
Thank you so much, Hope, for that awesome introduction. I've honestly never sounded cooler. And thank you all for being here today and tuning in to the virtual presentation of my master's project. It really means a lot to me to be able to show you guys what I've done over the last 2 years, especially during these crazy times. So thank you again. I would just like to start by having you guys look at the image that I have up on the screen. This picture was taken by Luis Ardrich in Buenos Aires, Argentina. And I like this picture a lot because it captures two natural phenomena that I think are really cool. One of which is something that you guys may be familiar with or have seen before, and that is the Milky Way, which is composed of the billions of stars in the galaxy. The other feature that is also in this image, but is something that you guys may not be as familiar with, is this vertical column of light on the center of the screen, and that is called the zodiacal light. Now, this is commonly seen right before sunrise or right after sunset, and in places where there's little to no light pollution. The zodiacal light is actually caused by sunlight that's been scattered by the microscopic particles orbiting the sun in space. Much of these particles are believed to be leftovers from the process that created Earth, as well as the other planets in our solar system approximately 4.5 billion years ago. The collection and the analyses of these dust particles were some of the main motivations behind my master's project, which is titled Particle Background and Methods for Cosmic Dust Collection at Manoa Observatory, which is located on the Big Island of Hawaii. So just to go over the outline of today's presentation, first I'll be going over what cosmic dust particles are and why we want to collect them in the first place. Then I'll be going over some of the previously used cosmic dust collection methods, as well as some of the problems that come along with those methods. I'll then be going over our main objectives. First, the long-term goals of our research program, as well as the main objectives of my master's project. Next, I'll be going over why we think Manoa Observatory is the perfect place for this type of collection. Then I'll be going over our methodology, which is divided into 3 segments: the collection phase, the processing phase, and the analysis phase of our samples. I'll then be diving onto the results and discussion sections before wrapping it up with a conclusion and future work. So on to the introduction. What are cosmic dust and why do we care? Well, cosmic dust, also known as extraterrestrial dust or space dust, refers to microscopic particles that exist in outer space released by dust-producing bodies such as comets or asteroids. On your screen are just examples of cosmic dust that were collected in previous efforts. The first particle on the left is a particle that is showing a popcorn-like or fluffy morphology. And it got that name because, as you can see, within that one particle, the individual grains can be easily seen, resembling popcorn kernels. This type of morphology is indicative of a particle that is likely cometary. The particle in the middle has slightly elongated grains and has a flaky or plate-like texture, and that is most likely due to some form of alteration. This type of texture is indicative of a particle that is likely asteroidal. The very last particle to the right is a particle that has been completely melted, most likely due to atmospheric entry heating, and then resolidified into a little sphere called a spheral. So once again, these are just examples from past collections. Approximately 40,000 tons of these types of particles enter the Earth's atmosphere and reach its surface annually. And we're particularly interested in the particles that come from comets because they form on the outermost portion of the protoplanetary disk. This disk, pictured on the top half of your screen, is a rotating disk of gases and dust surrounding a newly formed star, which in our case is the sun. Because comets form on the outermost portion of that disk, as highlighted by the diagram on the bottom portion of your screen, they would have been furthest away from the heat source and would have experienced the least amount of alteration. Studying these minimally altered particles can give us clues to the initial conditions and materials present during the earliest stages of our solar system. These types of studies are possible using analytical microscopy techniques, which we do here at the Advanced Electron Microscopy Center here at UH, which is then led by my advisor, Dr. Hope Ishii, as well as Dr. John Bradley. So although we have the tools necessary to study these samples, the main issue is collecting pristine samples in the first place. Aside from them being microscopic, cosmic dust that enter our atmosphere are immediately obscured by the natural and anthropogenic dust that we have on Earth. Natural dust include pollen or volcanic glass, and anthropogenic just means any dust produced due to human activity. These particles are also subjected to atmospheric entry heating, and sometimes this heating can either partially or fully melt these particles and alter their composition before they get resolidified into little spheres called spherules, which I showed you guys earlier in the presentation. Contamination also happens during the collection process, and any of the processes used to remove that contamination can further alter the grains. Finally, leaching, or another form of alteration, can occur due to prolonged exposure to water, ice, or snow. So before I go over some of the previously used methods of cosmic dust collection, I just wanted to show you guys a schematic of the Earth's atmosphere. There have been cosmic dust collections done in space, in the stratosphere, in the troposphere, as well as in deep sea sediments in the oceans. The bottommost portion of the troposphere is this region called the planetary boundary layer, which is approximately 2 kilometers above mean sea level. Below this imaginary line, there's a lot of turbulence because the direction of the wind is greatly affected by the Earth's topography. There's also a large flux of terrestrial particles. So you essentially wouldn't want to be collecting cosmic dust from this region. The higher up you go, the more consistent the winds are, the less terrestrial flux there is, and the higher the chances of you collecting a cosmic dust particle. However, the more challenging the collection process also becomes. So now I'll be going over the previously used cosmic dust collection methods, starting with space collections. And a good example of that is the Stardust mission, which was launched in 1999. Now, the Stardust was the first spacecraft to return extraterrestrial material from outside of the moon's orbit to Earth, and the samples were returned to us in 2006. However, in space, these particles are actually traveling at such high speeds, causing them to have a high impact velocity with whatever material we're using to collect them. This high impact velocity can then cause physical alteration or sometimes even a complete vaporization of these particles. To combat this issue, these types of missions use a material called an aerogel, which acts as a cushion and an adhesive to hopefully preserve that particle. What ends up happening, however, is that these particles end up embedding themselves deep inside this aerogel material, causing them to be hard to locate. On top of that, these types of missions don't happen very often, and when they do happen, the samples get returned to Earth several years after the initial launch of the mission. So there's just extremely limited collection. Moving on to magnetic sorting, where some scientists have used magnetic sampling materials that they've dragged across the seafloor to hopefully collect cosmic spherules that have settled in deep sea sediments. And a good example of that is the cosmic muck rake used by Don Brownlee in 1979. However, as I mentioned before, these spherules get their sphere shape due to the heavy alteration and melting. And so their elemental compositions are not representative of their compositions when they were initially formed. Also, prolonged exposure to ocean water would have caused some leaching effects. Scientists have also gone to cold regions such as Antarctica to collect cosmic dust that have embedded themselves in snow or ice cores. What they do is they collect ice cores, such as the picture I have up on the screen, or snow, and then they melt this and then collect the cosmic dust that have been embedded using a robotic vacuum, such as the ones used by the US Army Cold Regions Research and Engineering Laboratory. However, this heating of the snow or the ice cores can actually alter the chemistry of the grains. And again, exposure to ice and water for an extended period of time causes leaching. Finally, I'll be going over today's standard methods, which are called stratospheric collections, where they use high altitude aircraft, such as airplanes that go up approximately 20 kilometers, or stratospheric balloons that go from approximately 30 to 40 kilometers. And they collect cosmic dust from that region because there are minimally altered particles and there's low levels of terrestrial pollution. However, they use collection media that actually contaminates the samples, such as silicone oil. And again, any processes used to remove this contamination can further alter the grains. Also, these types of collections are very infrequent. So as you can see, there are advantages and disadvantages to all of the methods that I have talked about so far, which then brings us to the main objectives of our project, starting with the long-term goals of our research group, which is to be able to develop an inexpensive Earth-based collection method that can provide us with the most pristine cosmic dust samples possible. With this collected data, we want to be able to create an automated scanning electron microscopy, or SEM, searching technique. And I'll explain later what SEM is, but essentially we will be able to handle large amounts of data, and we can rapidly discriminate between extraterrestrial material versus non-extraterrestrial material. To achieve these long-term goals, I first have to achieve the main objectives of my master's project, which is to be able to characterize and categorize the terrestrial background particles that we will also be collecting during this process. We also want to be able to identify and analyze several extraterrestrial particle candidates. Moving on to our collection site, as I mentioned before, we are collecting at the Manoa Observatory located on the Big Island of Hawaii, highlighted by the red star on your screen. Now, the reasons why we think this is a good place for collection is because, as most of us know, Hawaii is one of the most isolated population centers on Earth, approximately 4,000 kilometers from California and 6,500 kilometers from Japan. We also have our sampler installed at a high elevation of 3,500 meters, and on top of that, Mauna Loa experiences katabatic winds, which is when at nighttime the cool air flows down mountain, bringing clean tropospheric level airs down to our sampler. We think that the combination of these things should give us relatively clean air compared to the rest of the world, and on top of that, our setup allows for inexpensive and frequent continuous collections. Also, we know that the Big Island is already home to several astronomical observatories, such as the Manoa Observatory, and then the Keck and Gemini observatories in Mauna Kea. This is important because we can then ask them if there are going to be meteor showers happening, and we can turn on our sampler during those events to hopefully collect particles from those events. The katabatic winds and the low terrestrial particle population at Mauna Loa has also already been previously utilized. Scientists have been depending on the same clean air to measure atmospheric carbon dioxide levels at MLO since 1958, which is commonly displayed as the Keeling curve, which I have up on the screen. So again, just the x-axis is year and the y-axis is parts per million of atmospheric carbon dioxide levels. This site has also been a proven site for extraterrestrial particle collection, as demonstrated by Kenneth Farley's study in 2001. What he did was he measured helium-3 to helium-4 ratios of his collected samples, and he found elevated helium-3 and helium-4 ratios consistent with samples that have spent a significant time in space and have been altered by cosmic rays. Looking at the plot, x-axis is helium-4, y-axis is helium-3, and each individual dots are the ratios. And as you can see, most of his samples fall between the pure extraterrestrial line and the pure terrestrial line, so they're a mixture of the two. So again, these are just examples as to why we think Mauna Loa Observatory has a high potential to collect cosmic dust particles. Moving on to our methodology, which, as I mentioned, is divided into 3 segments: the collection phase, the processing phase, and the analysis phase. I'll be starting with the collection phase. So here is an image of our high volume air sampler installed at 3,500 meters in Mauna Loa Observatory. And now I'll just be going over some of the key components of that sampler, starting with the anemometer, which determines wind speed and wind direction, and I'll explain later why that's important. We also have a timer which controls how long our sampler is active for, a vacuum pump which samples the air at an airflow rate of 1.4 cubic meters per minute, a pressure gauge, which displays the current airflow rate, the filters where our particles get collected, and then a protective cover that protects our filter from elements such as strong wind or rain. Going over the collection parameters of our sampler, again, our airflow rate is 1.4 cubic meters per minute. We have our anemometer set, so it has a 90-degree opening pointing uphill, so that's plus or minus 45 degrees from the downwind direction during katabatic winds. We have our wind speed limit set so that it is over 1 meters per second, and we have a timer set to collect only at nighttime when the katabatic winds are happening. So essentially, 3 things have to be met for our sampler to even activate. Number 1, the timer has to be on, meaning the katabatic winds have to be happening. This air has to be traveling at least 1 meters per second, and it has to be flowing within that plus or minus 45 degree or a total 90-degree opening. If one of these conditions aren't met, then our sampler will turn off. And what this does is that it ensures collection only during the most optimal conditions. As far as how often we change our filters, we have multiple options. We can depend on the pressure gauge. So if our pressure gauge reads that the airflow rate is less than 75% of the initial 1.4 cubic meters per minute rate, then we can change our filters. We can also do fixed number of hours. So if we reach a certain number of hours, we can change our filters. Or we can do time collection. So when our collaborators at NOAA, or National Oceanic Atmospheric Administration, let us know that there are meteor showers, then we can turn on our sampler to collect particles, or hopefully collect particles from that specific event. Moving on to the sample processing phase of our methodology, on your screen is an image of the filter that we put in our sampler. It has a surface area of 390 square centimeters, and it is just slightly smaller than your average sheet of paper. A high magnification SEM, or scanning electron microscopy, image of that filter shows the 5-micron diameter perforations, or little tiny holes as indicated by the black circles on that blue box, that allow air to pass through while trapping particles that are larger than 5 diameters, or sometimes slightly smaller than 5 diameters. We then get this filter and turn it into a smaller 11.5 square centimeter circle that we will put in our instruments. And so this next image then is what our samples look like before we put it into our instruments, which I will talk about later. But first, we use 2 different processing methods to get that big filter into that small circle. The first method is called the concentrating method, which is actually conducted by our collaborators at the University of Kent in the United Kingdom. What they do is they put our filter above a nozzle that is attached to a vacuum pump, and then they wash our filter in a circular motion using high purity deionized water. What this does is it carries all the particles in that filter to the center. They then let this filter dry, and then they cut out this small circle and mount it onto an aluminum sample stub, which they then sent to us for carbon coating and analysis. The next method is the stamping method, which is actually conducted and we developed in our lab downstairs. What we do is we place a double-sided carbon adhesive tape onto a sample stub, and this stub is then lightly and gently pressed or stamped in multiple locations in our filter. For our particular sample, we stamped it 4 times. Now I will just be going over the 2 samples that I analyzed for this project, a pre-Kilauea eruption filter and a post-Kilauea eruption filter. So they got that name because obviously the pre-Kilauea eruption filter was installed before the 2018 Kilauea eruption event. And then the post-Kilauea eruption filter was installed after that 2018 eruption event. The reason why we chose these 2 filters and not filters that were installed close to or during that event was so that our filters wouldn't be overwhelmed by all the volcanic particles that would have come from that event. So now just going over the dates, the pre-Kilauea eruption filter was installed from September 5th to November 8th of 2017. The post-Kilauea eruption filter was installed from March 12th to July 30th of 2019. As far as the total number of hours that the sampler was activated, for the pre-Kilauea eruption filter, it was activated for 493 hours. And for the post-Kilauea eruption filter, it was activated for 1,016 hours. As far as processing methods, the pre-Kilauea eruption filter was processed by our collaborators using the concentrating method, and then we processed the post-Kilauea eruption filter using the stamping method downstairs. As far as the concentration factor, the pre-Kilauea eruption filter has a concentration factor of 34, and we got that number simply by dividing the initial surface area of the big filter by the surface area of the small final sample, and the number was 34. For the post-Kilauea eruption filter, the number 4 was from the amount of times we stamped our sample stub onto the exposed filter. However, as you can see, the post-Kilauea eruption filter was exposed for over twice as long as the pre-Kilauea eruption filter. So we multiplied that concentration factor by 2. So we have an effective concentration factor of 8 for the post-Kilauea eruption filter compared to the pre-Kilauea eruption filter. Moving on to the sample analysis portion of our methodology, starting with the first instrument we used, which is the FEI Helios NanoLab 660 Extreme High Resolution Dual Beam Focused Ion Beam, or just dual beam for short, dual beam fib, or just the fib. And so what that can do is, this is an image of our dual beam fib. So it has a sample chamber and electron columns and ion columns and an injection gas needles pointing towards the same spot on the sample. Here are just additional images. The top image is a profile view of our sample chamber that's currently open, which is where our sample goes. This chamber is then vacuum sealed and depressurized to the appropriate conditions before analysis can even begin. The bottom half of that picture shows the interior of the fib, showing the electron column, ion columns, and a bunch of injection gas needles, again pointing at the same spot on the sample. So what these fib can do is, number one, scanning electron microscopy, or SEM. And what that gives us is a high resolution imagery of our sample. That gives us information on its textures, morphologies, and some of the features that are visible on the surface. This can also do energy dispersive X-ray spectroscopy, or EDS, and that has elemental analysis and mapping capabilities. Finally, when we have a particle of interest, we want to be able to create a thin section of that particular particle, and we use the fib for that. So the fib is capable of doing scanning, transmission, electron microscopy, or STEM, sample preparation, which I'll explain later in the talk. So now I'll just be going over the first thing we did, which is to image the sample using SEM. So what we did was we took random regions in the sample and we saved the coordinates so we can always come back to those spots later if we want to access them again. An image was then taken at the appropriate magnification so that approximately 50 or so particles are visible on the screen, which we then call a section. The reason for the number 50 was so that we can analyze a lot of particles within one section, but not too much so that it gets too overwhelming when we're trying to label each individual particles. After we have a section, we then label and number all the particles in all of our sections. For this particular sections, there are 59 particles visible. And after that's done, we then get a high magnification image of each individual particle in all of our sections that we collected. After that, we perform energy dispersive X-ray spectroscopy, or EDS. And again, that is performed on every single particle in all of our chosen sections. And that gives us their elemental composition, so pretty much all the elements present in that sample and their relative abundance. For some particles that are a combination of multiple particles stuck together, we took multiple measurements so that we can get accurate measurements. And then we quantified our results with and without carbon simply because we carbon coded our sample. And so quantifying our results without carbon allows us to look at the other elements that may have been masked due to the skewed carbon numbers. So just circling back, the first two things we did using the fib is SEM, which gives us imagery and information on morphology and texture, and then EDS, which gave us the elemental composition. These two things combined allow us to categorize the particles that we have in our samples. So now moving on to the particle categorization portion, we first divided our particles into two categories: extraterrestrial candidates versus non-candidates or background particles. So extraterrestrial candidates are particles that have compositions that fall within a factor of 5 times the CI chondrite composition, or essentially the composition of the sun. The reason for the high factor number of 5 is so that we don't exclude any particles due to uncertainties caused by physical overlap of the grains in our samples. What we did was we took the element to silicon ratio of the most abundant elements in the CI chondrite composition, and that includes oxygen, magnesium, silicon, and iron. Obviously, the silicon to silicon ratio will just be 1 for all of our candidates, so we didn't look at that. We focused on the oxygen to silicon, magnesium to silicon, and iron to silicon ratios. If all those 3 ratios fall within a factor of 5 of the CI chondrite composition ratios, then we flag that as a potential ET candidate for further analysis. We also looked at single mineral grains with compositions that are inconsistent with local origin. So in our case, it's Hawaii. And a good example of that is an ensitite particle from a prior collection effort at MLO as well, that has a significantly high magnesium levels and low iron levels, inconsistent with what we would expect the volcanic particles in Hawaii should have. After we separated those two into two categories, we then look at the bulk background particle types and categorize them even further by looking at their particle morphology and elemental spectra. Once we've done that, we go back to our extraterrestrial candidates and examine them further and for further analysis. These most promising candidates have compositions that fall within an even lower and stricter factor of 2 times to 3 times the CI chondrite composition. So now when we have a particle of interest, we want to create, as I mentioned before, a thin section of that one dust particle to put into the next instrument that I'll be talking about later. So I'll be going over that process right now. So image A shows a particle of interest, and you can see the green rectangle is the region that we want to make a thin section of. The reason why we chose that region was because not only are we going to be able to get the particle, we can also study the material that is on top of the surface of our sample. Once we have a desired region, we then deposit platinum on top of that green rectangle, as you can see on image B. And this platinum will act as a shield and a protective barrier for when we are cutting both sides of our particle. Image C shows both sides of the particle being milled or cut. And as you can see, the platinum is still there protecting our desired region. Once we've done that, we insert a micro manipulator needle near our sample, which is shown on image D. And then we weld that needle onto our sample using platinum. Once it's been welded, the underside of our sample is then cut off and cut free from the substrate, and this needle is then pulled out. Image E shows our needle being inserted onto a copper grid, which will go into the next instrument. So as you can see, there's our needle. The small tiny dot on the center is the sample, and then the thing at the bottom is the copper grid where it is attached to. So after it's been attached to the copper grid using platinum, the needle is then detached. And so image F shows a zoomed in image of image D, which shows our sample being attached to the copper grid, and then the needle has been cut free. This sample then goes onto or in a double tilt holder, which will go to the next instrument. Again, I'll explain that later. And on the middle of that double tilt holder is where the copper grid will go, where our sample is. So on the red box is an example of a copper grid. It's not the grid that we use, but this is just an example photo of the holder with the grid inside. A zoomed in image of that grid shows the letters A, B, C, which is just useful for navigation because the sample is so small. So it allows you to find your sample quicker. On the middle of that second image that I show is a blue box where the actual sample is. As you can see, it's very tiny. And so a zoomed in image of that is the actual sample that we analyzed for this project. And so you can see that it's been thinned out to the appropriate thickness required for our next instrument, which is approximately 100 to 150 nanometers. The next instrument we use where we put the double tilt holder is the FEI Titan 3 G2 60 to 300 dual aberration corrected scanning transmission electron microscopy, or Titan microscope for short. So again, what STEM can do is it gives us a high resolution, bright field, and dark field imagery of our thin section that we just created. We can also perform EDS, which is similar to what we did with the FIB. However, this time we're looking at several sections in the thin section as opposed to just the surface of the sample. And then finally, we can also perform selected area electron diffractions, which essentially gives us patterns where we can analyze and figure out the crystal structure of our sample. Moving on to the results and discussion portion of this talk, starting with the percentages of the extraterrestrial particle candidates in both the pre-kilowave eruption filter and the post-kilowave eruption filter. So for the pre-kilowave eruption filter, we were able to analyze 152 particles, to which we found that approximately 6% of them, or 9 particles, are extraterrestrial particle candidates. For the post-kilowave eruption filter, we analyzed 173 particles and determined that approximately 12% of those, or approximately 20 particles, are candidates. We also did this measurements using a stricter number factor of 4 times and 3 times the CI chondrite composition, just to see the numbers. And I'll show you guys that on the next slide. So again, highlighted right now is the factor of 5 for pre-kilowave and post-kilowave, with 6% and 12%. For a factor of 4, now there's 3% for pre-kilowave and 7% for post-kilowave. And then for an even stricter factor of 3 times the CI chondrite composition, there's less than 1% for pre-kilowave and approximately 5% for post-kilowave. Now, as you can see, the stricter the factor is, the less extraterrestrial particle candidates there are, which makes sense. But again, we used the higher factor of 5 to not exclude particles due to uncertainties in our measurements caused by a physical overlap of grades. Again, after I've divided them into two categories, we further analyzed the non-candidates or the background particles, which I will talk about here. So starting with the pre-kilauea eruption filter, again with a factor of 5, we got 6% ET candidates, 38% clay-like, 20% feldspathic, 14% pyroxene-like, 10% silica-rich, 9% carbon, and then 1% for oxides, spheroids, and uncategorized particles. Moving on to the post-Kilauea eruption filter, we were able to find 12% ET candidates, 36% clay-like, 17% feldspathic, 14% silica-rich, 9% carbon, 5% sulfates, 4% pyroxene-like, and then 1% for oxides, carbonates, and uncategorized categories. Looking at these two filters side by side, you can see that they generally have the same particle categories. However, there are some notable differences. The first being the ET candidate percentages. Again, 6% for pre-Kilauea, 12% for post-Kilauea. There's also a huge disparity in the pyroxene-like category, 14% for pre-Kilauea and 4% for post-Kilauea. And then finally, the post-Kilauea eruption filter showed approximately 5% sulfates, and we weren't able to find any sulfates at all in the pre-Kilauea eruption filter. So just to discuss those differences a little bit more, again, just as a reminder, I have them listed up above. Lower percentage of ET candidates for pre-Kilauea, higher percentage of pyroxene-like particles, and then no sulfates, and pretty much the opposite for the post-Kilauea. Higher percentage of ET candidates, low percentage of pyroxene-like particles, and then 5% sulfates. So some possible explanations for these differences. Number one, obviously we collected them in two different collection periods, approximately 2 years apart, to which different types of elements were just arriving in our samples, or in our sampler. Number two, these two filters were exposed for a different number of hours. And just as a reminder, the post-Kilauea eruption filter was exposed for over twice as long as the pre-Kilauea eruption filter. During this time, there may have been an extra meteor shower that could have possibly explained the spike in the percentage of ET candidates in the post-Kilauea eruption filter. Finally, we processed them using two different processing methods. Again, just as a reminder, the pre-Kilauea eruption filter was processed using the concentrating method with a water washing, and the post-Kilauea eruption filter was processed with a stamping method without any water washing. And so what we think is this water washing contributes to a potential breakup of the particles in our filters, as well as the loss of the more soluble particles such as sulfates. And that is a likely explanation as to why we weren't able to see any sulfates in our pre-Kilauea eruption filter. Now just going over representative images and particle spectra of each of the categories that we found in our two samples. So again, here's an image, and then to the right of them are just spectra, which gives us the elements that are present, and then the height of the peaks tell you the relative abundance compared to everything else. Starting with carbon-rich. So the carbon-rich particles ranged from having a morphology that is pollen-like or little spheres. For this particular example, it has a graphitic or graphite-like texture. And looking at the spectra, you can see that there is a high carbon peak and not really much of anything else. Moving down to the carbonate category, we look for particles to have an equally high carbon and oxygen peaks in the spectra. And this particular sample also has a high sodium peak. So this is likely a sodium carbonate. The clay-like particles tend to have a flaky or plate-like texture. And then they have a high oxygen peak in the spectra, and then a lot of trace elements also present, probably due to some weathering or alteration. For the feldspathic category, the morphology is varied, and then we looked for spectra that had oxygen, sodium, aluminum, silicon, and potassium. For oxides, we look for particles that have strong oxygen peaks and either a titanium or iron peak. So this is an example of a titanium oxide, but we were also able to find iron oxides. The pyroxene-like particles tend to have a blocky morphology, and for the spectra, we look for spectra that have oxygen, magnesium, aluminum, silicon, calcium, and sometimes iron. For the silica-rich particles, they are more angular in morphology, and then they tend to have a strong silicon peak compared to everything else, but sometimes they have other peaks as well, such as this one. The spheroid particles were indistinguishable based on the spectra alone, but if they have a sphere shape, then we lump them into a spheroid category. The sulfates are particles that have a high sulfur peak, just like this one. And as you can see, all the other particles barely have any sulfur peaks. And this one has a sulfur peak, which again was only found in the post-Kilauea eruption filter. And then if we had just no clue what they are based on spectra or morphology, we lump them in an uncategorized category, such as this one in the yellow box. Moving on to some of the promising ET particles that we ended up choosing. we chose 5 of them. Again, these ones have compositions that fall within a stricter factor of 2 times to 3 times the CI conrod composition. Images A, C, D, and E all have a clay-like texture and composition, and then image B has a texture and composition that is similar to an olivine. We ended up choosing this olivine-like particle as our most promising candidate that we wanted to perform additional analysis on, because again, it has a composition that fit within a really strict factor of 2 times the CI chondrite composition, and that includes the full particle as well as some of the material that is on top of the surface. And again, we just looked at the magnesium to silicon, iron to silicon, and oxygen to silicon ratios. Additionally, evidence of space exposure is just more easily seen in single mineral grains such as this one. So moving on to the STEM analysis of the thin section that we created. So this is the an image, a STEM bright field and STEM dark field image of that olivine-like particle where we created a thin section. The center of both of those images is the actual particle. The top darker region is the platinum protective cover that we put during the milling process. And then the bottom is the substrate where the particle is attached. So the reason for getting both the bright field and the dark field imagery is because some features in the bright field is not visible in the dark field and vice versa. And so getting both of these images and comparing them side by side allows you to not miss any potential features. As far as features that we were looking for solar flare tracks. And an example of that is this particle that was from the Hayabusa mission. This particle is an asteroid particle, and you can see that it has spent a significant time in space, indicated by the solar flare tracks that look like straight white lines going in different directions. So it doesn't have a normal pattern. Looking back at our samples, you can see that we don't see any of those solar flare tracks, indicating that we probably have not spent a significant time in space to get them. What we do see, however, are some of these features near the surface that are alteration or just surface material. So just looking at that a little bit closer, you can see that as the surface alteration labeled has a morphology that is different from the actual particle. There's also some material present that I'm going to circle with my mouse right here, which is likely the material that is on top of our particle before we created the thin section. So we wanted to do EDS measurements of this to look at these alteration and surface features to see if they may be chondritic. So as far as EDS measurements go, we took EDS measurements in 4 different areas of that portion of the sample. Areas 1, 2, 3, and 4. Areas 1 has a spectra that is consistent with an olivine particle, and that's similar to area 3. However, the main difference is area 3 is a thinner section of that olivine, probably due to some mistake during the thinning process. And then it also has some platinum contamination, most likely because of the platinum that we deposited on top when we were preparing the thin section. Areas 2 is consistent with an olivine that has been kind of been altered and kind of morphing into a clay-like particle. And then again, the spectra for area 4 is consistent with a clay-like material, and that is probably, again, that surface material that was on top of our sample. On your screen is a selected area electron diffraction, which we were also able to do. And so this gives us patterns where we can look for the crystal structure of our sample. To the left is the electron diffraction pattern that we got during the experiment for our actual sample, and this was along the 211 zone axis. This is then compared to a simulation that was done using the Crystal Maker software of an olivine particle along the 211 zone axis. Now, looking at the patterns, both the geometries of the patterns as well as the d-spacings or the spacings between the individual dots are a match. And so essentially, this is just an additional confirmation that our particle is indeed an olivine. To discuss those findings a little bit further, again, we got textures, elemental spectra, and crystal structure of our sample that all point to it being an olivine particle. However, we weren't able to find any solar flare tracks or any ion damaged rims that would mean that it has spent a significant time in space. Our sample also has a significant high iron content consistent with more of a terrestrial particle, and the surface coating, which we were hoping to be chondritic, turned out to be clay-like and not chondritic. With all that being said, this one particle that we conducted STEM analysis on is most likely terrestrial particles. With that being said, we still have a lot of other particles to look at, and we can hope that they may be extraterrestrial. Circling back to the percentages of the ET candidates that we got, again, for pre-kilo eruption filter, as I mentioned before, we got 6%. For the post-kilo eruption filter, we got 12%. These were actually lower than what we were hoping for, simply because, as I mentioned before, our collection site was in an isolated region, and then we employed really strict collection parameters. So why is there still a high percentage of background particles? Well, that can be explained by a study done by Sharma and Barnes in 2016, where they used a camera lidar technique to measure the wind direction at Manoa Observatory. And what they determined was that the katabatic winds at MLO has an upslope component, which they call the counterflowing air. This counterflowing air essentially circles back up and gets entrained in that clean downslope air. And what that does is that the terrestrial particles that get carried by this counterflowing air can get incorporated into what supposedly was that clean air that we were hoping for. This can potentially influence aerosol sampling at Mauna Loa and is a likely explanation as to why the percentages that we got for ET candidates were slightly lower than what we were hoping them to be. Now moving on to the conclusion and future work of my project, starting with some key takeaways. Using the high volume air sampling method in Mauna Loa allows for cheap, continuous, and easily accessible collection of particles without the use of contaminants such as aerogel or silicone oil, without the leaching effects caused due to prolonged exposure to water, ice, or snow. And it's done in an isolated area that experiences katabatic winds. On top of that, we can do time collections when our collaborators let us know that there are meteor showers, and we get constant atmospheric monitoring data from our collaborators at NOAA. Some of the things that we were able to achieve include, we were able to categorize the background particle population. We were able to determine that the stamping processing method was more effective than the concentrating method because it didn't have the water washing that contributed to the loss of the soluble particles and contributed to particle breakup. We were also able to identify several ET candidates, and although that one particle that we analyzed turned out to be not an extraterrestrial material, we were still able to develop a systematic methodology for sample collection, processing, and analysis during the course of this project. This methodology can then be further refined and then be utilized as a standard for future Earth-based cosmic dust collection efforts. Future work will involve gathering more data from our existing filters, both the pre-Kilauea and the post-Kilauea. And what that will do is I'll be able to fine-tune the particle type percentages that I presented earlier. There's also potential for us to find more ET candidates for future studies. Also, with this collected data, again, we want to be able to create an automated SEM searching technique, which again will give us the ability to rapidly discriminate between ET candidates and background particle, and we can handle large amounts of data. To put into perspective how much we will be needing this SEM searching technique in the future, here is an image of the sample, the 11.5 square centimeter sample that we put in our instrument that I showed you guys earlier in the presentation. On this sample is a tiny yellow box that illustrates the area that we were able to analyze in our sample. And if you can't see it, I don't blame you because it's very tiny. I'm gonna point to it using this arrow. And this area is actually 0.01% of this total area. But keep in mind that within this tiny little box, we were able to analyze a total of 320 or 150 particles for both pre-Kilauea and post-Kilauea. However, we really want to be able to analyze a lot of the sample in a more efficient way instead of looking at the particles one by one, which is what we did for our collection process. So this automated SEM searching technique will be really useful in the future. We also want to be able to examine other ET candidates that we have, again, using STEM to look for evidence of space exposure. And then we want to maybe get a percentage of the successful ET candidates that displays those features. And then also, perform oxygen isotope analysis on the candidates to confirm their origin. Finally, but we also want to be able to process our other filters, this time sticking to one method. And again, we deemed that the stamping method is the preferred method because it doesn't contribute to the overconcentration of the particles, and it lowers the chance of particle breakup as well as the loss of soluble particles like sulfates. Because we carbon coded our initial samples, we also want to be able to explore different sample coding options so that we avoid skewed carbon numbers in the future. Finally, we want to be able to optimize collection parameters of our sampler, such as getting a stronger vacuum pump that our filter paper can handle, maybe further decreasing the wind sector angle, perhaps even reducing the size of the initial filter that we use, and then maybe even raising the sampler higher off the ground with the use of stilts. And what this will do is that it will hopefully increase the extraterrestrial to terrestrial particle ratio in future collections at Mauna Loa. So that concludes my presentation, but before I get to questions, there are just some people that I have to thank and acknowledge. I first want to thank my advisor, Dr. Hope Ishii, for taking the chance to meet and providing me with this awesome opportunity of being part of a research group and working on this project. Hope has been an amazing mentor from the moment I got accepted to the university up until the very end. And everything I've learned from her, I will take with me in the future world or in the professional world. It's been a pleasure working with you over these last 2 years, and it's such an honor being your first master's student here at UH. I also have to thank my the other members of my committee, Dr. John Bradley and Dr. Tom Shea. John Bradley did a tremendous amount of work with helping me analyze the particles in my sample and categorize them. And he's also been an amazing mentor throughout these 2 years. And then Tom Shea was an invaluable source of information, particularly when it came to volcanic particles present in my samples. Additionally, I want to thank the members of our research group. First, Leanne Teodoro, who was a former undergraduate here at the Earth Sciences Department. Her work as an undergrad actually served as one of my first introductions to the MLO Cosmic Dust Project. And then Ken Teotaki, who's a postdoc researcher in our group, trained me how to use the instruments that we have properly and also helped a lot with sample preparations. So thank you, Kenta and Leanne. And then I want to thank our collaborators, first at NOAA, for allowing us to use the Manoa Observatory for our particle collection, and then particularly Matthew Martinson, who maintained our sampler and sent us filters on a regular basis. I also want to thank our collaborators from the University of Kent in the United Kingdom, Dr. Penelope Vojnikevich and Luke Elsbrook, for processing some of our samples. Finally, I have to thank some of my biggest supporters, which are my family and friends. First, I have to thank my family and friends from the Bay Area, California, for being amazing cheerleaders from afar and for always being there for me to talk to when I felt like I missed a little bit of home. I also have to thank the amazing friends that I met here in Hawaii over the last 2 years, both within the department and the university, also outside of the university. I always knew that moving to Hawaii was going to be an amazing experience because, I mean, duh, it's Hawaii, but it's really the amazing people that I met along the way that have made my experience here an unforgettable one so far and have made this place feel like a second home. And then lastly, my parents are here today. I don't know if you guys have seen them, but my parents, Romeo and Maria Janabi, I just want to thank them so much. So, you know, my parents left their comfort zone and their family and friends in the Philippines to move me here in the States at a very young age, to expose me to opportunities that I probably would not have been exposed to had we not moved. And I just know that as much as as hard as I've worked over these last few years, I would not be anywhere where I am today if not for their sacrifices and the support that they've given me, not only in my academic pursuits, but as well as all the aspects of my life. So thanks, Mom and Dad. Give everyone a nice wave. And so with that being said, I hope that all of you guys tuning in learned something new today that you thought was interesting. And if anyone has any questions, I will try my best to answer them. Thank you.
Thank you, Angelo.
I need a drink of water.
So those
I'm
of you
shaking,
who
look.
haven't used the raise hand button before, there should be a button called participants, and if you click on that and go to your name, there is an option. There should be an option either at the bottom of that participants window or next to your name under more to raise your hand.
How do I see that? Oh, participants, got it. I see a hand from Linda Martell. Unmute. Hello.
Okay.
Linda.
Hi, Janae. This is Steve. I'm dipping into Linda.
Oh, just kidding.
Right now, I got a couple questions.
Of course.
For going over the whole sample that you've got, it seems like you need to get some automated image analysis done.
Absolutely. Right.
And is that's something that's planned to do?
Yeah, so my advisor, Hope, actually submitted a grant proposal for NASA, and that includes getting that automated searching technique. However, it just hasn't been approved yet, and it's very costly. So we're waiting for it to get approved, and hopefully we can get that software in the future for a more efficient analysis, so we can just explore more of the sample.
Okay.
Yeah, this is Hope. I gotta butt in and say that we had hoped that we would have the particle detection algorithms. That it's basically a software add-on to our FIB SEM capability. We hoped we would have that during Angelo's project, and we did not. So he has done a massive amount of work. It's impressive.
Yeah, I got that sense. Okay, the other questions had to do with the sampling. And
Yeah.
I was wondering, this is two-part, if
Sure.
the sampling was done during the same time of day, was it 24 hours a day for each one? And
Sure.
also the sampling was done at different times of the year. And I was
Right.
wondering what the effects you think there might have been on the different seasons when the sampling was done.
Right. So as far as your first part, which is the time of day, again, we have our timer set so that it only collects during nighttime when the katabatic winds are happening. So we don't collect at all during the daytime when the wind direction is kind of swirly and all over the place. We're hoping for that nighttime cool downflowing air. So that's the answer to the first part. As far as the seasons go, I'm not quite sure how to answer that, but obviously the flux of cosmic dust is not consistent. There will be more cosmic dust particles when there are meteor showers, and we just can't predict that unless our collaborators let us know.
Okay. All right. That was it for me.
Okay. Thank you. I have to look at the hand thing. Diamond. I'm gonna unmute Diamond. Hi, Diamond.
I didn't have a question. I was just clapping because that was a great presentation.
Oh my God. Thank you. I appreciate it. There's a hand from Trista. I'm unmuting Trista.
Actually, same thing as Diamond. That's the hand clapping.
Oh, that's hand clapping. Damn it.
Great job.
Thanks. Garrett. Garrett has a hand that's not clapping.
Hi.
Hi, Garrett.
Fabulous presentation. I learned, well, I learned almost an infinite amount because I knew very little about this before.
Thank you so much. I appreciate it.
It was a really fun presentation. But I did
Thank
want to,
you.
I'm just really curious, however, is it possible that a particle does not melt and is sampled in a popcorn form? I'm just amazed that that's ever possible.
Right. So that popcorn stuff is most likely collected at a higher elevation. And then also, if the particle is lighter, then it may have a slower speed entering our atmosphere. So it doesn't have as much of that atmospheric entry heating component where it gets fully altered. And so we're hoping that some of the lighter particles that settle through aren't going through the atmosphere that fast. And so that's probably why it's possible to get particles that aren't little spheres or aren't heavily altered. At least that's my understanding.
Okay, great. Thank you.
So not just lighter, but lower density. They experience less pressure coming through the atmosphere.
Yeah, quite remarkably, well, first of all, particles come in at a distribution of velocities, but it is remarkable that some particles come through with what appears to be minimal heating. By minimal heating, I mean a couple of hundred C for about 20 seconds. And there are various theories as to why they survive, but certainly density is a factor. There's some evidence that organic material outgasses, or some of the organic material outgasses and forms a sort of a gaseous ablation shield. And finally, we do know that some particles come in, have maximum heating temperatures from their mineralogy of about a couple of hundred degrees C. That may be a kinetic effect rather than a real temperature spike effect.
Maybe if you don't mind, a follow-up question. So I imagine the spherical particles are pretty common. I mean, that's what I would guess. And those would be easier to pick out.
Right.
Right.
Right, correct. Yeah, so like, again, some of the older collections did collect these cosmic spherules, which is, I mean, it's amazing because they're extraterrestrial particles and we're analyzing them. However, because they're in this altered form, then they probably don't have a good representation of the original compositions that they would have had when they were formed. So although it's a bonus that we can study them, studying the ones that aren't melted or aren't altered will give you I guess, a better understanding of the original composition.
But if they're easier to pick out
Right.
simply by their morphology, you might
Yeah.
get us, at least in a statistical sense, you know, get an idea of how many extraterrestrial particles you're actually sampling.
Absolutely, and those aren't necessarily ruled out as like non-candidates. They're just not like the best samples. Like we still want them, obviously.
Great,
Yeah,
thank you.
they also tend to be, the spherules tend to be formed from larger particles. So it's not necessarily sampling the same population.
Mhm.
Tom, I'm muting you, Tom. Is that a hand?
Unmute myself.
Okay,
Okay,
there
I
it
just
is.
unmute. I think we have to do 2 unmutes.
Oh, I
So
see.
Angelo,
Okay. Yes.
yeah, I think I muted myself ahead of time.
Yeah, I hear you now.
Okay, so nice talk. Thanks very much. I did learn a lot.
Thank
I was
you.
kind of wondering about the period between the meteor shower and the time that it's actually recorded
Right.
or detected. So it seems
Right,
like
I
that
think-
would be very complex to determine that.
Absolutely. I think there, from what I understand, is definitely a lag. Like you don't turn on the sampler when it is happening. I think it's a week or 2 weeks. I'm not sure on the exact dates, but there's definitely a lag before you're able to, even hopefully collect particles from that event. You wouldn't want to be turning on your sampler when it's happening currently. There is definitely a lag.
Yeah. Okay. So the follow on there is, well, I was thinking there could be value. Some meteor showers are peaked and have 2 peaks actually. So it'd be nice to be able to sample one peak or the other. But those peaks tend to be maybe a day or 2 apart. So it sounds like it's below the resolution of when the particle would arrive.
Right.
So,
Yeah.
okay.
And again, and for this particular, the 2 samples that we collected, we weren't focusing on the meteor showers. Like they weren't the time collections where Noah was like, okay, there's a meteor shower, you guys should turn on our sampler. This was just going on continuously every night. It's collecting within the time frame that I explained earlier. So yeah, I guess we can do other collection that specifically focuses on turning them on, after that lag time. But these samples were not that.
Okay, thank you.
Yeah, you're welcome. Is that it? I hope so.
Do you have any other questions, speaker?
Oh, there's a hand raised.
Oh.
This is Steve Martell again. I just wanted to
Hi,
say,
Steve.
I'm echoing what Garrett said. I thought this was amazing. It's fantastic that you can do this stuff in terms of both the chemistry and the thin sectioning in the imagery at that scale. And a very nice presentation as well.
Thank you so much. Thank you.
Okay, well, if we don't have any additional questions now, we're going to go ahead and adjourn the public portion of the session. And the committee will rejoin Angelo. So what I think we're going to try to do is you all can either leave meeting, except for Tom and John and Angelo and I. And if you can't figure out how to do that, then Lily knows how to encourage you out. But thank you so much for attending.